Hi everyone. In the previous two lectures on the course Microelectronic Circuits, we discussed about negative feedback amplifiers and how to find loop gain in a negative feedback circuit. Now, while discussing some examples on how to find the loop gain, we took an example where we encountered a positive feedback circuit. And in that circuit, we spoke about stability and we said that for that circuit to remain stable, the loop gain should be less than 1. Now, in this lecture, I'll try to clarify that in slightly more depth than what we did in the previous lectures. Also, to fully talk about the frequency or the stability of a feedback system, we'll have to talk about the frequency response of feedback systems. So I'll reserve that for later lectures. Right now, I'll just give a very brief idea why did we impose this condition in a positively fed-back amplifier. To do that, I'll start with this very simple negative feedback amplifier. So we know it's a negative feedback. If you traverse the loop fully, the phase shift should be 180 degrees. The loop gain is given, the overall gain is given by A by 1 plus A beta. I'm going to assume that the circuit is always in negative feedback now I'm going to change the loop gain A beta from 0 to infinity. So I'm changing A beta from 0 to infinity, but I'm not changing its sign, so the feedback is still a negative feedback. Now, even though I'm changing A beta, of course the overall closed loop gain will change, but the system is always stable. So this is an unconditionally stable system. There is no condition under which the system can become unstable. So as long as it's a negatively fed-back system and A beta is greater than 0, it will give a bounded output. And of course, we are assuming beta or 1 by beta here is finite. On the other hand, shown here is a positively fed-back system or a positively fed-back amplifier. Now in this system, the gain is given by A by 1 minus A beta. Now we can see from this expression itself, if A beta equals 1, then the gain becomes infinity. And it's not very obvious from this example. If A beta is greater than 1, we will later see that the system's output can grow unbounded, or the system can become unstable. But as long as A beta is less than 1, if A beta is less than 1, this value will converge, A by 1 minus A beta will converge to a finite value. So we can say the system is stable. So therefore, we'll use the word conditionally stable. So this is stable under certain conditions as long as your loop gain A beta is less than 1. So to explain this and understand this in slightly more greater depth, we will use a more practical model for the amplifier. So I'm going to introduce just one pole in the amplifier, and we'll see what happens to this pole as the loop gain is varied. Now the closed loop transfer function, generally to find the closed loop poles, we just have to equate 1 plus loop gain equal to 0. So that's your denominator of the transfer function. So 1 plus loop gain here is simply this term, 1 plus A beta by 1 plus S by omega p. And if you solve this, you get the pole as omega p into 1 plus A beta. So this is something we are already aware of. We said that if you take a single pole system and put it in negative feedback, the bandwidth extends by a factor of 1 plus A beta. Now this plus here is for a negative feedback system. Now as I vary the loop gain, here that's the parameter we are varying. As I vary the loop gain to infinity, starting from say 0 to infinity, the pole it starts from minus omega p and it becomes more and more negative. Now we know from basic Laplace transform theory that if the pole is in the right of S plane, then the system is unstable. System becomes unstable. But as we vary or increase the loop gain, we can see that the pole is further in the left of S plane, moves further to the left of the S plane. So which means this system can also be said to be an unconditionally stable system. So it doesn't depend on the value of the loop gain, whatever be its value, it's still a stable system. Of course, the pole locations will vary, but it's still a stable system. In fact, what I've drawn here is simply the root locus. For those of you, if you're aware of it, it's just a root locus of the system. So from that, we can directly see that this is the locus of the closed loop pole of the system, and we can say that the system is stable. On the other hand, if you consider a right of plane pole, a positively fed back system, so here it's positively fed back, and now we are going to write the loop gain. The characteristic function is going to be 1 minus loop gain equal to 0. The sign difference comes because of the positive feedback. And now the pole location is given by minus omega p into 1 minus a beta. Here instead of 1 plus, it's now 1 minus a beta. Now if we plot the trajectory or the variation of the pole as a function of a beta or the loop gain, as you increase it, how does the pole move on the S-plane? We can see that shown here in red, as you increase the loop gain, the pole starts moving towards the j omega axis, and eventually it crosses the j omega axis when a beta is greater than 1. So the system here is stable as long as your loop gain is less than 1, and it becomes unstable in this region. So here we can see in a positively fed back system, the conditional stability condition actually comes into the picture. So the system is stable for these values of loop gain. If your a beta is less than 1, system is stable, otherwise the system becomes unstable. And this is a good model. We just assume that there is some pole in the system. So any pole, it can be a parasitic pole in any circuit. And using that, we just showed the conditional stability of a positively fed back system. Now, to further illustrate the point better, I have considered a second order system. So it's simpler to assume two poles at the same frequency. So we are going to consider two poles at the same point and then show and see what happens to the closed loop poles, both in a negatively and positively fed back systems. First, in a negatively fed back system, the loop gain, the characteristic function is going to be, a characteristic equation is going to be 1 plus loop gain equal to 0. So solving that, you'll actually get an expression 1 plus s by omega p the whole square equals minus a beta. So this is just the loop gain is going to be, the characteristic equation is going to be 1 plus a beta by 1 plus s by omega p the whole square equal to 0. And by just rearranging few terms, you will get the expression for the pole as minus omega p into 1 plus minus j times root of a beta. So it directly follows from here, from this equation, you get this equation here. Now what you see here is that the poles are complex. The moment you introduce negative feedback, the open loop, the poles were real, but negative feedback, the poles have become complex. We will talk in greater detail about this at a later stage when we discuss frequency response of negative feedback systems. But right now, we'll just look at the mathematics and see what happens to the closed loop poles. As you vary the loop gain, if you see the real part remains unchanged, but only the imaginary part changes. As you increase the loop gain, the imaginary part, the root locus moves, or rather the poles move further into the complex part increases, and the poles become complex conjugates. We started with real poles, but the poles soon became complex conjugate. So you should expect the impulse response will look something like this. So we'll have a decaying sine wave that looks like this. As you further increase your loop gain, what would happen is that the poles will further move higher along the j omega axis. What it simply means is that the envelope is going to remain the same, but you will now have more ringing before it decays down. So generally these poles are called high Q poles. As far as analog engineers are concerned, even high Q poles are concerned. So we don't generally prefer to have the response which undergoes several oscillations before it decays down. So that's very close to instability. Okay, it's not unstable, but still this is something that we don't prefer. But in spite of all of this, the poles still remain in the left of S-plane. So again, if you have a two-pole system, we began with a two-pole system, and we showed that both the poles in a negatively fed back system, still it's an unconditionally stable system. So even though I'm varying the loop gain, the system is unconditionally stable. Now we'll consider a positively fed back system. The characteristic equation here, instead of 1 plus, it's going to be 1 minus, and therefore you'll end up getting this equation. If you see here, previously this term was negative here, so when you took the square root, we got the imaginary number I. Okay, the poles were complex, but now it's no longer negative, so poles will be real, and the poles will be given by minus omega p into 1 plus minus root a beta. So you have two poles. One pole is at minus of omega p into 1 minus root a beta. The other pole is at minus omega p into 1 plus root a beta. As you increase the loop gain, you can see both the poles are real. This pole will become more and more negative. And as you increase the loop gain here, you can see after a point, this pole will become positive, or it will become a right of plane pole. So that's what I've shown here. The trajectory of the poles, one pole is going to move in this direction, the other pole is going to move towards the j omega axis. And when a beta becomes equal to 1, that's the point where the pole just touches, one pole just touches the j omega axis. The other pole becomes minus 2 omega p. And after that, if a beta is greater than 1, then the pole enters the right of plane. So therefore the system then becomes unstable. So this is a simple way of understanding why in positively fed back systems we need to ensure that the loop gain is always less than 1. It's easier to visualize when you assume just 1 or 2 poles, then it's much easier to explain it away. So this is why when we were analyzing feedback circuits, in a positively fed back circuit, we impose this condition for it to be stable. Also, just to finally clear one doubt, I think some of you posted on the comments, that this resistor here, I analyzed this circuit here, it's a current reference circuit. We will talk in more detail about this at a later stage, both band gap and current references. But right now, the question posed was, there is a resistance here, and we know that from Store's degeneration, this resistor is going to offer some kind of a negative feedback. So I have drawn a mathematical model for this MOS and resistor together. I have shown here it's a negatively fed back system. In fact, so there is negative feedback here, and then there is also positive feedback. So aren't there two kinds of feedback in the circuit? The first question to answer is that yes, there is negative feedback, but this is like a local negative feedback. There is a local local loop here. This MOSFET and the resistor forms a local negative feedback circuit. But as a whole, you can treat it as one simple transconductor. So there is, we can't say that there is both negative and positive feedback in the circuit. Okay, there are circuits, for example, some band gap references or some niche, probably in analog charge pump PLLs, we have some architectures of charge pump which uses the positive, both a combination of positive and negative feedback. But even in all those circuits, negative feedback will either dominate, or if positive feedback dominates, we will ensure that the loop gain is always less than 1. That condition has to be ensured. I gave you some simple reasons why it should be ensured. Now to answer this, I'm just going to show, for example, let's say we have a negatively fed back system, a positively fed back system with a local negative feedback loop. Okay, there can be some feedback factor here. So let's say we have some locally, there is some local negative feedback loop, but overall loop here is a positively fed back loop. So that's what I think this model, probably this circuit will be better represented by a mathematical model which looks this way, which has a local negative feedback and a overall positive feedback loop. It really doesn't make a difference because it's the overall positive feedback which dominates. This overall negative feedback local loop can be reduced to a single transfer function or just some gain A1. Now for this overall system to be stable, you have to ensure A1, A2 into beta 2 should be less than 1. Because there is a positive feedback in this loop, this condition has to be satisfied. So that's it. We'll talk in greater detail about the feedback or the stability of negative feedback systems in the upcoming lectures.